Okay, so in the last class, we were discussing about the intrinsic carrier concentration of a semiconductor, which is, in fact, the product, which is the most interesting uh, quantity here, so which is given by this product of number of electrons in the conduction band and number of holes in the valence band. So is given by this expression, and Nc and Nv are basically the density of states or effective density of states in conduction band and valence band respectively, and Eg is your band gap. So this product is this Np is always constant at a particular temperature. And this is always true for any semiconductor material, irrespective of whether it is intrinsic or extrinsic. This product should be always constant. So that means if you increase the number of electrons by doping, so automatically the number of to keep this product constant, so number of holes would reduce. And similarly, if you increase the number of holes by doping trivalent atoms, then you also increase. So you increase the number of holes and you reduce the number of electrons in the material. And this is how you can create this N and P type semiconductor. So which brings us to this extrinsic semiconductor. They are known as the extrinsic semiconductor. And the first we are discussing about the N-type semiconductor here. So this picture here, what it shows, it's an N-type semiconductor. So you have basically a pentavalent atom, so with valence state 5, such as arsenic or phosphorus. And when they make a bond in or dope in silicon, so they make these bonds, the 4 electrons, they make this covalent bond with 4 of the sp3 hybridized electrons of silicon, and 1 electron here remains free. Okay, so this electron basically is not anymore attached to the arsenic atom anymore, so it becomes free and contributes to the conduction band of the semiconductor. In this case, it is the silicon. So so what you have is basically this arsenic atom. So behaves like as if it has arsenic plus ion with 1 free electron uh, in the conduction band, and this arsenic ion is basically it's not movable or immobile, and the free electron is of course will contribute to the conductivity of the material. Now, what is the binding energy of this electron? So the binding energy of the electron we can calculate using the simple Bohr model, which is given by E will be equal to me star e to the power 4 divided by 8 epsilon square epsilon r square h square, which like in terms of the binding energy of hydrogen, you can write something like me star by me divided by 1 by epsilon r square, and this is in electron volt. So if you use, for example, arsenic in silicon, so what will be the binding energy of the electron, even for any pentavalent atom for that matter, either arsenic or phosphorus. So typically the Me star is equal to 1/3 of the free electron mass. Epsilon r of silicon is about 11.9. So if you substitute that, so you will get a value of 0.032 electron volt. Okay, so this is basically the binding energy of the electron in uh, when arsenic is doped in silicon. Okay, so this is the binding energy. But the average thermal energy at room temperature, so the average thermal energy will be is of the order of 3 kBT. So at room temperature, when T is equal to 300 Kelvin, so this energy will be of the order of 0.07 electron volt, of that order. Okay, so that means you have this thermal energy at of the material is much higher compared to the binding energy of the electron, and that's why this electron will be free, and that electron free means it will go to the conduction band of the material, and that is how you will get this n-type semiconductor. So this is a schematic picture of this energy diagram of that this how you get extra electrons uh, in the conduction band due to doping. So here what is shown in the crystal, so you have this arsenic uh, ions which are localized, and then they act as a donor, so they are called as donor or donor atoms because they are donating the electrons, and at room temperature, so this energy, this 0.03 electron volt, you can get it from the thermal energy, and these electrons become free and part of the conduction band. So now let's say if we have so if we have, let's say nd, which is equal to the number of dopants per unit volume or the dopant concentration. So we can say in case of doping, when the number of electrons that we will have in the conduction band will be almost like equal to the number of dopants. So if we assume that all the dopants are ionized at room temperature, which is the most likely case, so the number of electrons in the conduction band will be equal to n of t. And here we are also assuming that number of dopants are much higher than the intrinsic carrier concentration of the electrons. So in this case, uh, and that is what typically happens in n-type semiconductor. So you have the number of electrons in the conduction band is almost equal to the number of dopants that you have in the material. And what will be the number of holes in that case? So it will be Ni square by N of D. Okay, so because this is, again, it's a constant that we will have. And the conductivity will be given by, the conductivity is equal to E N mu E plus E P mu H. But since your number of electron is equal to number of dopants, so it is E N D mu E plus E P mu H. And since this number is Nd is much higher than your intrinsic carrier concentration, so Nd will be much higher than Ni, or that means Nd is much higher than your P, the number of holes, and therefore sigma will be dominated by the conductivity of the electrons. So the contribution of hole to the conductivity will be minimum, and the conductivity is mostly determined by the conductivity due to electrons. So sometimes this is known as the majority charge carrier. So in N type, it is the electron, and the holes, this P, are known as the minority charge carriers. So this is when we are talking about N-type semiconductor. But if you say it's a P-type semiconductor, so in that case, the number of holes will be larger because so we will see we have the acceptor atoms, and then the number of holes will be larger, and in that case, P will be the majority charge carrier if it is a P-type semiconductor. Now, there is a very interesting thing which we will discuss now. What is the temperature dependence of this concentration, N? So we say N will be equal to N of D, but will it be always the same? This number of electrons in the conduction band, will it be always equal to the number of dopants? It is not. And it depends on actually the temperature of the material. So let's look at the temperature dependence of the carrier concentration. And basically, there are three regions we will look at. So we say there are the three temperature regions, and we will look at how the carrier concentration N changes due to temperature. So let's look at the low temperature regime. So which we say the temperature is less than Ts. We call it a low temperature regime or low temperature range. And what happens when you are at low temperature? The most likely the thermal energy, the average thermal energy is less. So that means the ionization of the dopants will be low. So you will not be able to ionize all the dopants, and therefore the number of electrons will not be that large in the conduction band. Okay, and in that case, your number of charge carriers or concentration of electrons, since we are talking about the electrons, so will be given by this term. So the first term is very similar to what we saw earlier for electron, for intrinsic concentration. Only difference here is what we have is this delta E term. So we have, we have replaced Eg, this band gap, by delta E. Why? Because when you look at this picture here, so the excitation will happen from, so it is not happening, so in case of the intrinsic carrier, the electrons has to jump from the valence band to the conduction band, and therefore we were taking the difference EC minus EV, which is equal to our EG, the energy band gap. But now the excitation will actually happen from the band which is close to the conduction band. This arsenic, the energy band will be, or these are the energy level of arsenic will be close to the conduction band, and therefore the energy difference between EC and ED, that is what will decide how many electrons will be in the conduction band. So this delta E, what we are writing here, is nothing but EC minus the energy level of the dopant, in this case arsenic. Okay, so this is known as the ionization range. Okay, so this is the ionization range. So when you are below this temperature Ts, so basically your electrons will be getting, the ions are getting ionized, and this is so not full ionization has not happened, and this range is the ionization range. Then when you are above Ts, so we call it the medium temperature range. So that means our temperature is something between our Ts and Ti. And so what happens above Ts? So when you reach Ts, so all the dopants will be ionized basically. So you will reach a temperature where all the dopants are ionized. So when you are above Ts, so that means there will be no more increase in the number of electrons, even if you are increasing the temperature. And since all the dopants are ionized, so N, the number of electrons in the conduction band, will be equal to the number of dopants. So this is the one which we discussed, or I talked about when we discussed about the conductivity earlier. So here we defined this conductivity as E N, or N T NDE mu T. So in this temperature range, the conductivity is given by this, will be dominated by the only electron concentration. Because all the dopants are ionized here, and this region is therefore known as the extrinsic range. Okay, and this is the most important for any semiconductor for device application. So when you want to know what is the temperature range of the device, so this is, it has to operate in this extrinsic range. So if I talk about a diode or any semiconductor device, will operate in this range. Okay, so because at this, within this temperature range, your carrier concentration, or your the charge carrier concentration, in this case electron, is equal to the number of dopants. So this is the ideal operating temperature range for your device. Now what happens if you increase further the temperature? So when your temperature is greater than your Ti, so this is, will be definitely your high temperature range. Okay, and what happens here? So now if you are at a higher temperature, it is possible that now more and more electrons will get excited from the valence band, because now the thermal energy will be much higher. That means your this delta E term is equal to the band gap, and therefore electrons from valence band will jump to conduction band. Earlier it was not possible. Okay, earlier what was happening, only electrons from the dopant energy level, so they were going into the conduction band. So now if the temperature is high, in that case electron will jump from the valence band to the conduction band, and your carrier concentration, the intrinsic carrier concentration, will be much higher than your dopant carrier concentration. Okay, and basically this the carrier concentration or conductivity and everything will be dominated due to this factor Ni. Okay. This means the material actually will behave more like a intrinsic semiconductor, because now the carrier concentration or the conductivity will determined by the number Ni. So this is known as a intrinsic range. So earlier it was the extrinsic. So the first was ionization range at low temperature. So we have the ionization that is taking place up to a temperature Ts, after which all the dopants are basically ionized, and up to a temperature Ti, your carrier concentration will be equal to the number of dopants or the number of the dopant concentration, and that is your extrinsic range where your device normally operates. And if you increase to a higher temperature, again electrons will jump from the valence band to conduction band, and that will be again like a intrinsic range. So when you are, the purpose of doping is like, for example, when we say silicon, and we saw in case of silicon, when we are doping arsenic, at room temperature, we can actually ionize all the dopants. And that's why silicon is a very good, like used for many devices at room temperature. So similarly, germanium as well, or gallium arsenide. So most of the semiconductors, like when you dope, so if the doping, if the doping happens or the extrinsic range is at room temperature, so that is what ideally you want. Okay, so this is a temperature dependence of the carrier concentration, which decides in which temperature range you will operate your device. So. Yeah, here is a picture, schematic picture of that. What I described is 3 temperature regions. So you have the low temperature regime where the ionization taking place only. So you have arsenic ions, and most of the electrons are bound to the arsenic atom here. Okay. Now, as you increase a temperature where T is between Ts and Ti, so all the arsenic atoms are now ionized. So the electrons, then they are all going into the conduction band. Now, if the temperature is too high, when temperature is greater than your Ti, then electrons jump from the valence band to the conduction band, and therefore it becomes behaves like more like a intrinsic semiconductor. So it is not, and I mean, in that case, the doping doesn't matter anymore, or the conductivity is not determined by how many dopants you have. Okay, so the same thing, conductor, we can do it for the p-type semiconductor as well. So here, so this what we have shown is for taking example of silicon and arsenic. So you can have phosphorus as well as one of the dopant in case of silicon. So here for p-type semiconductor, the example is a boron, which is a trivalent atom. That means now the boron will form a bond. So 3 of the electrons will form a bond with 3 of the electrons of sp3 hybridized electron of silicon, and the one electron in the silicon remains, which is not anymore bonded to boron anymore, and therefore the boron will make sure there will be a hole, which actually, or absence of electron, which will act as a charge carrier in this p-type semiconductor. So the hole or the absence of electron basically will contribute to the conductivity which is present in the valence band. Okay, So these are the schematic pictures, and everything what we did will remain the same. Here again, this is a schematic band structure of that. So what we shown here, so you can also calculate what is the binding energy in case of a p-type. And this is about this 0.05 electron volt. So that means now the electron from the valence band of silicon will jump or will go to the B minus, which is the boron, and will get trapped there. So it will stay there and it becomes immobile. And in the process, it creates this hole in the valence band, which will be basically your the mobile charge carrier, which will move in the valence band. And again, this 0.05 electron volt is close to the thermal energy, average thermal energy at room temperature, and that's why you can these electrons can go to the boron site and they stay there. And anyway, this boron will be a immobile charge. It's an ion, so will stay there. It's a localized ionic state there, and only you will create these whole states which are mobile. Okay, so the same discussion we had for n-type semiconductor holds good here. So in this case, your sigma will be E n A, or we call it NA in mu H. So NA is here number of dopants, or here it is called as acceptors. So in other case we call it a donor, and here we call it number of acceptors, Na. And if you look at the temperature range of the operation, you will exactly have the same picture, and the operation will the device will operate when your temperature is less than Ts and or less than Ti and greater than Ts, within which your the number of holes here, P, will be equal to N of A. Okay, so in this temperature range, so the number of holes will be equal to the number of acceptor ions, and this will be the dominant term for the conductivity, where you would like to, this is the extrinsic range where you would like that your device operates. So in most of the cases, this N, the number of electrons, even if we are talking about the extrinsic semiconductor, the number of electrons and number of holes, P, they are actually very small compared to the number of states that are available in the conduction band, and that's a number of states available in the valence band. So what I mean by that, so N is always less than or much less than this NC, and P is always much less than NV. So this is what we this NC and NV are basically your, these are basically your density of effective density of states in the conduction band and valence band respectively. And since this is the situation, N is much less than NC and P is much less than NV, so we can actually apply this Boltzmann statistics there. So instead of the Fermi-Dirac statistics, and that is what we used to calculate the number of electrons and holes. And these kind of semiconductors are known as non-degenerate semiconductors. Okay, so most of the semiconductor that is that are used in devices. So like you are making a diode or transistor. So in all those cases, the semiconductor is most like a non-degenerate. It is extrinsic but non-degenerate semiconductor. That means the number of electrons and number of holes are much less than the available states in the conduction band and the valence band, and that's why you can apply the treat them as a classical electrons and use a Boltzmann distribution for that. But if you dope it heavily, so if you put a lot of dopants, so in that case your ND, let's say your donor or acceptor concentration is, let's say, of the order of 10 to the power 20 atoms per centimeter cube. Okay, so if it is a heavy doping, so this is known as heavy doping. So typically the dopant are like 10 to the power 10 or 10 to the power 12 atoms per centimeter cube. Or even you can go up to 10 to the power 15, let's say. But if you are too high, 10 to the power 20, 10 to the power 19 or 10 to the power 20 atoms, if you put in the your intrinsic material. So now if I put 10 to the power 20 arsenic atom in per cubic centimeter in silicon, so in that case, the number of electrons will be much greater than the available states NC, and similarly the number of holes will be even greater than the number of states available in the valence band. So in that case, the situation will be very different. Okay, so you cannot apply the Boltzmann distribution, and basically you have to treat electron again as a quantum mechanical particle. They have to follow the Pauli's exclusion principle. So you have to apply the Fermi-Dirac statistics, and many of the things that are actually true for intrinsic or extrinsic semiconductor, they do not hold true. So this kind of material are known as degenerate. They are known as degenerate semiconductors. So if you dope a semiconductor heavily, then in that case you increase the number of electron and holes compared to the number of states available, and those semiconductors are known as degenerate semiconductor. And in that case, so your whatever we did earlier, like this, the mass action law, NP, that is Ni square, which is constant, will not be true. So it will not, you cannot apply this mass action law in a degenerate semiconductor. Okay. And so it is not like they don't have any application. So this degenerate semiconductor have a lot more application. For example, they are used in a laser, diode. They are used as metal contacts. Actually, mostly they are used as very similar to metal. So what happens if you do a heavy doping? So in that case, the material actually behave more like a metal. So so what happens? There's arsenic. The number of now arsenic atoms will be much closer, for example, and then there will be an overlap of the atomic orbitals of arsenic, and they will also form a energy band actually. Okay, and that energy band will overlap with the conduction band of the intrinsic semiconductor, and in fact the material will behave like a metal. Okay, and in that case you can put or use this degenerate semiconductor as a metal contact with semiconductor. So the same semiconductor, so you can dope depending on the doping level. So you can make it an extrinsic semiconductor, which will be used in a N and P device, okay, a diode or something in normal device. You can then dope it heavily and use it as a metal contact as well. Okay, so this is instead of using a normal metal like Typically, you would use copper or aluminum as a metal contact. Instead of that, or like that is like copper, aluminum, or gold or silver that you use. Instead of that, you can actually use a heavily doped semiconductor, a degenerate semiconductor as a metal contact. And that is actually used in semiconductor devices. Okay. So another point which we will discuss about the semiconductor properties is the band gap. So what we will discuss about is a direct and indirect band gap. Okay. Uh, so uh, so before we go to this, so I want to discuss something in regard that. So let's say further down. Okay. So when so any semiconductor material, like when we discuss about a semiconductor properties, the electronic properties, so we will discuss about its conductivity or mostly its mobility, okay? Then the charge carrier concentration, and another thing, so they are more related to the electrical transport, or how the electron will move or hole will move in the, or the charge carrier will move in the material. But there is also another property which is very important for semiconductor and its application. This is the band gap. So when we take like a schematic diagram of a semiconductor, so we said this is our valence band, okay? This is your conduction band. So this is EC and this is EV. And you can excite electrons from the conduction valence band to the conduction band. So you'll have electrons here, either due to doping, or so if it is not due to doping, so normally if it is an intrinsic one, so you can excite from the valence band to the conduction band due to the thermal energy. You can also have a process where this electron will jump back to the valence band, and in the process it will release a photon, okay, or a light with a frequency or energy which is equal to your band gap. Okay, so this process is known as recombination. So the process of creating electrons or getting electron into the conduction band, which is known as a generation. And when this electron is de-excited, so it comes back to the valence band, and it will emit most likely a certain energy, which is the difference between the energy level of the valence band and the conduction band, which is nothing but the band gap. So this process is known as recombination. However, there is a very we missed one point when we discuss about this, that we say electron, so when it jumps from conduction band to valence band, so it will release certain energy. And why it is doing that? Because, and in the process it will basically conserving the energy. So there is a energy conservation is happening there. So if I say this energy of electron in conduction band minus energy of electron in the valence band will be equal to Eg. So this is your energy conservation. But what we have missed is the conservation of momentum. So when this excitation or de-excitation process happens in an energy band, so we said energy, each electron has an energy, also it is associated with a momentum, P, right? And when this generation and recombination processes are happening, so energy has to be conserved. Similarly, your momentum also should be conserved as well. And what is the momentum of an electron? So we said E is equal to P square by 2m. So that means each electron will can be defined by a specific momentum, okay, and correspondingly this speed and so on. And there is a different representation of electrons in a band when we talk about the momentum. So each electron is basically, it's like a wave, right? So it's like a quantum mechanical representation. It is like a wave function, and it has a the wave, it's like a traveling wave which has momentum which is associated with a wave vector k. So that means your momentum p is normally written as h cross k in case of an electron in a crystal. So this is known as a crystal momentum. It is not the momentum of the crystal, but the momentum of electron in the crystal. Okay. And if you look at this h cross k, what is h cross? H cross is a representation we do like h by 2 pi. So this is how h cross is written, and k is 2 pi by lambda. So p, if you look at this expression and substitute that, so you'll get your familiar expression p is equal to h by lambda, where lambda is your de Broglie wavelength of the electron in that energy state. So each energy, so electron as so when we are considering it's a particle, so it's in the quantum mechanical wavelength lambda, and the momentum is h by lambda. So in fact, you can write momentum as h cross k here, where k is a wave vector. Okay. So therefore, each electron, so when this recombination process happens, or excitation or de-excitation happens, so energy has to be conserved and momentum has to be conserved. So here this picture actually shows that. So now, if your electron is recombining, so in the recombination process, let's say electron jumps from the bottom of the conduction band to the top of the valence band. So please pay attention here. So it is jumping from the bottom of the conduction band to the top of the valence band. And the value of k, this k value, or h cross k for that matter, the momentum is exactly the same. So in this process, so when electron jumps from here to this, so you have the electron here, then they are jumping to this here. So in this case, your delta P is equal to 0. There is no change in momentum. So it is happening exactly at the same K value. So in other way, we say K CB of the electron, or H cross K CB, is equal to H cross K VV of the electron. Okay. So this is the momentum is conserved. So such materials are known as a direct band gap material. So in the direct band gap material, so example is here gallium arsenide, for example, or most of the compound semiconductor, indium arsenide. Okay, so these compound semiconductors, so they are direct band gap semiconductors. But if you take a silicon, like elemental semiconductor, like silicon or germanium, so this picture is different. So when you plot the energy as a function of momentum, so we are plotting energy as a function of momentum. So the top one is your conduction band, and the bottom is the valence band. So the conduction band is representing your electron. This is all parabolic, so always we are making it parabolic because of this relation is proportional to p square, or another way it's h cross square k square. So it is a E is proportional to p square, or this h cross this k square dependent. So this is therefore a parabolic behavior. So this valence band is representing the parabolic behavior of electron as a function of momentum in a parabolic manner for electron, and this one is for this behavior is for hole. Okay, although we are calling it a valence band, and we are saying, so it is like an inverted or the mirror image of the behavior in the conduction band. The hole behaves exactly like a opposite way to electron, and therefore what we are plotting here is the energy band of the hole. So hole has a minimum energy, so the minimum energy is here, and then as you increase or you go down, the energy of hole will increase. But in the opposite case, what happens? So the electron energy is maximum here, and when you go down, electron energy is going down. Okay, so this is why this is inverted. And in case of silicon and germanium, what happens is there is a shift in the bottom of the conduction band and the top of the valence band. So this is your top of the valence band. This is a valence band. This is your conduction band minimum. So they are at different k values or momentum. So the momentum, the state of the electron corresponding to the momentum where the minimum of conduction band is different where your maximum of valence band is. So there is a difference. And in this case, if a transition happens in this case, let's say you say my electron jumps from here to here, electron. So in this case, okay, you can say energy will be conserved, but momentum is not conserved. Your delta P is not equal to 0. That means your H cross KCB is not equal to H cross KVB, because the electron has a momentum of H cross KCB here, but when it comes to this point, the momentum is H cross KVB, and the momentum state is different. So the momentum is not conserved, and therefore this process normally cannot happen. This recombination process will be a forbidden one. However, there is definitely recombination taking place. And how it is happening? So you need a third body which will help in this conservation process. And what is that? So you have something known as a trapping center. So you have a trapping center in the material. So again, we represent it in a schematic way. So you have the conduction band and the valence band. So now this is a indirect band gap material. So now electron cannot jump directly to the valence band. So what happens? So electron will, so you have some trapping center here, where these are basically can be some defect or impurity atoms. Okay, so this trapping center can be due to the defect or impurities, and where they have energy levels, they are localized energy levels, and the electron from here now will jump here. Okay, and then after some point or some time, it will again go to the valence band and go to a whole position which is like available. That means a empty electron state is available, and then the recombination will take place. Okay, so this is how they can then conserve the momentum. So how do we write that down? So normally you will write it down as like H cross K CB is equal to H cross K dB plus some momentum term due to the trap uh, center. So the trapping center acts as a will take the extra momentum that is will be released during this recombination process. And many times it happens due to this defect or impurities, and also it can so now there will be a energy that is also will be released, which is not in terms of photon or light, rather it is in terms of the energy will be much lower in that case, and the energy will be, now if you look at the energy, the energy in the conduction band, energy in the valence band, plus some energy, let's say omega, and this energy omega is will be given to the, will be released like a lattice or atomic vibration. So it is not anymore released like a light or a photon, rather it will be released as a form of lattice or atomic vibration, because the energy is much lower. So it is not like a direct photon that is generated in the process, in the recombination process. So this is your indirect band gap semiconductor. And these direct band gap semiconductors, and therefore they are used in light emitting diodes. So when you make a light emitting device, so you would like to use a simple direct band gap material, because of this energy and momentum conservation is simple. So gallium arsenide is that's why it's used for this light emitting diodes. So you don't normally use you don't use silicon or germanium for that case. So compound semiconductors are used as light emitting diodes. Okay, so we'll stop for today. Any question? Okay, so if not, so thank you.